Good morning. I'm Jody O'Sullivan from the Department of Electrical and Systems Engineering, and it's really been an honor for me to be here, and I want to congratulate my colleagues, Jim and Gershin, on doing a great job of organizing this conference and bring together many old friends and colleagues like Bijoy of the department back for this. It's been great. So in our final session here, it's going to be kicked off by Fabio Pasqualetti. He had his PhD in mechanical engineering and was a postdoctoral researcher at the University of California, Santa Barbara. And since 2013, he's been an assistant professor of mechanical engineering at UC Riverside.
Thank you, Joseph, for the introduction, and thank you, Jerzy and Sheila, for the invitation and for the wonderful workshop that I've organized. I must be honest, so last night, after seeing all the talks, I really got nervous. I said, how can I keep up with this quality? And I kept thinking, how do I tweak my slides? How do I make it better? And eventually I gave up and fell asleep. So here's the result. And hopefully, yeah. So I'm looking forward to hear your feedback and comments on whatever ideas you may have. So today I'll be talking about synchronization. Synchronization is a topic that probably you all know about, and actually you probably know more than what I know at this point. It's a topic that has been around for a long time. In fact, the first time that it was observed as a phenomenon was probably the 17th century. But since then, synchronization is making its way into many applications, many scenarios. In fact, you can talk about synchronization in biological and natural systems. You can talk about synchronization in technological systems. And these two scenarios are all very different from each other, but what they have in common is that there's usually a network. There's usually a large population of units, components, and these components show to some extent cohesive behavior, to some extent. Now, a big question that has been around for a long time is what are the mechanisms that allow synchronization in one of these networks? So of course you have different topologies, you have different network models, different dynamics, but is there a common mechanism behind all these phenomena that we observe? And the literature is in fact abundant, and I really hope that with this short slide I don't make anybody angry here, but really the literature is huge. So you have books, you have publications, different fields, different community, and so on and so forth. So at this point you may wonder what's left to do. What I argue, and hopefully by the end of this talk I will have convinced you a little bit about this, is that there are still many questions that we need to look at. And in fact, if we think of studying the brain, understanding the brain, and eventually controlling the brain, many of the results that have been developed in the context of synchronization are still insufficient. And here's a few reasons why. Well, big chunk of the literature focus on full synchronization. So full or complete synchronization is a phenomenon where all the units synchronize all together. However, this is not always the case. In fact, both in biological systems and in fact in the brain as well, as I will illustrate next, you have synchronization in clusters, not complete synchronization. So that's one first difference that rules out most of the work, or many of the works that have been developed in synchronization. The second aspect is that the notion of synchronization that is commonly used is very rigid. So units are synchronized if they are exactly on top of each other when they evolve over time. Well, this is a very convenient definition because it allows for mathematical derivations and conditions to be discovered. However, in practice, this doesn't happen. So if you introduce notions of synchronization that are a little more relaxed, then all of a sudden results are critically lacking again. And then, conditions are sometimes mathematical or algebraic, and they give you very little insight into the structure, the underlying structure of the network itself. And instead, this is our premise. So that's where we start from. We want to understand whether the organization of the network itself has a role and how I can leverage that organization in order to enforce a synchronization pattern that I like. And this will be clear in a few slides, hopefully. And then, again, most studies are somehow descriptive. So they take a system, they take a network, and they give you conditions, algebraic or geometric or some kind of condition that tells you if and how synchronization will emerge. But control paradigms are, in fact, much more limited. So we have seen a talk yesterday from Jeff, in fact, where they were doing desynchronization or synchronization in cluster in some models of oscillators. However, the question is much more broad. In fact, if you want to enforce a pattern that is a little more complex, then how do you do such a control? And again, how do you exploit the geometric and graphical structure of your system in order to achieve such a goal. So I argue that cluster synchronization or pattern synchronization, I will use both names with the same meaning in this talk, is in fact very relevant. For instance, if you look at social networks, well, it's very common that individuals, they group into, they form smaller groups, for instance, when they try to reach an opinion. Not everybody agrees on the same opinion. Cluster synchronization is also important in power grids. Well, in this case, it has a negative effect because you want all the generators to be synchronized for power to be generated. But if you lose synchronization, it's likely that some generators will form clusters. So understanding cluster synchronization in this context could help you prevent blackouts or other loss of power in your networks. And most importantly, and I think that's probably the most interesting focus for this workshop, if you take fMRI scans of the brain, you see that regions of the brain are in fact coherent with each other. They exhibit a certain behavior that is synchronized over time. But the pattern of synchronization that you observe is first not complete, and it also changes depending on the condition of the brain, the states of the brain. For instance, there are different patterns that are associated with different neurological disorders. And in fact, I mean, you could go as far as saying that if you are able to control pattern synchronization in the brain, perhaps you are able to predict and transition between healthy and disease states. Well, this is a big jump, but I'm just going to throw it there as an idea. And in fact, what I'm going to do from now on is just looking at a little bit of mathematics behind this problem. But that's the underlying motivation, and I just wanted to give you the overall 5, 10, 15, or 50, or 100 years ago from now. So key question, how do we understand the role of the topological structure, graphical structure in a network to shape pattern synchronization? So to analyze this question, we start from a very simple model. So first of all, we need a network. For that network, we take DSI images of the brain. We parcellate the brain into regions. We assign a node to each region of the brain. And then we connect regions based on the white matter structure that we observe from these images. So at the end of the day, we do have a network. We associate a dynamical equation with each of the nodes of the network. And for this dynamical equation, we choose the Kuramoto models. So that's a very simple model. As we learned already, most models are wrong, probably all of them. But let's start from something. So let's take the Kuramoto model. This model has 3 main ingredients. Well, theta I is going to be the phase of the oscillator. Omega I is what's called the natural frequency of the oscillator. So that's an intrinsic property of the oscillator. And then you have coupling between oscillators. So coupling is enforced by these terms Aij, which describe an adjacency matrix. So encoded with this Aij, you really have your network structure. So let me point out that the networks that we are considering here are heterogeneous in the sense that oscillators may be different from one another, and that means that this natural frequency could be different from one another. Topologies that we consider are very general. It's not fully connected. In fact, some of these Aij could be 0. So some links could be missing, some links could be weaker than others could be added or removed, and so on and so forth. So this model is in fact fairly general, with the assumption and limitation of the dynamical equations that we consider. And again, we'll return to that point a little bit more. So when trying to analyze cluster of pattern synchronization, the first thing that we need is a little more formal definition. So we're going to take our network, so consider, for instance, this toy example that is going to be recurrent in this talk. We're going to partition the nodes, for instance, in colors. So you see one cluster is the blue one is the orange one, and one is the green one. So in this case, I have 3 partitions. I'm going to say that my partition is phase synchronized if the phases within each cluster are the same over time. And again, this is a rigid definition, as I discussed before, but I'm going to relax it as the talk goes. And also the partition is frequency synchronized if instead of the phases being the same within each cluster, the frequencies satisfy this problem. So I have a graph. I divide the graph into groups. I look at the nodes within each group. If the phases are cohesive, exactly equal over time, then it's phase synchronized. If the frequencies are the same, then it's frequency synchronized. So if you take only one partition, that's exactly the canonical definition of synchronization. So everybody is synchronized together. So what's more here is that you're dividing into groups and you're allowing a little more freedom in define your landscape. So two questions that we're trying to understand: how does the structure, in the sense of this topology and AIJ, enforce pattern synchronization, and how do I leverage this structure in order to shape the synchronization pattern in a way that I want, healthy state, for instance. So, okay, let's look again at this very simple example, and let's look at a sufficient condition for synchronization. Well, I want my two oscillators, for instance 4 and 5, to evolve in the same way. Why don't I take the difference of their dynamical equation? So if I take the difference, there are two terms that pop up. One is the difference of their natural frequency, and one is the difference given by the coupling with external nodes or clusters. So if I can make this difference 0, and I can make this coupling, difference of coupling 0, well, these two oscillators will evolve together. Again, that's a sufficient condition. It's really simple. And it turns out that, so again, in order to make them evolve together, you just set their frequency to be the same. You force the neighboring nodes to belong to the same cluster, in this case 3 and 6. And you force the coupling to be the same as well. So weight 4, 3 and 5, 6, which are the weights over these links, to be the same. So this seems also almost like a joke, but it turns out that this condition is necessary and sufficient. So you can actually generalize it to more complicated structure, and you can find a condition on the adjacency matrix, which is basically some sort of balance condition between different clusters, that ensures that the partition, so the pattern that you want to be, that you want synchronization to converge to, is actually forward invariant. So if you start there, the oscillators are going to evolve with the same pattern that you expect. So you need two properties. One is that the frequencies within each cluster are the same, and then these connections with neighboring clusters are somehow balanced. So if you look again at this example, for instance, and you look, say, at this orange cluster, 3 and 6, then you have, of course, the frequency 3 and 6 must be the same, and also the sum of the weights coming, say, from 1 and 2 to 3, and 7 and 8 to 6 must be the same. Now notice that I do not, in fact, it's not necessary to have the weights which are exactly the same. It's the cumulative effect over the cluster that needs to be the same. So that's why you have this summation over here. I also want to stress that the patterns that we are able to characterize and enforce with this type of conditions are such that nodes may actually be not even connected with each other. So if you see here, 1 and 2 is actually responding to 7 and 8 and synchronizing with them. And there's not a direct path between them. And this feature, I believe, is very important because if you look at fMRI scans, you really have regions of the brain that synchronize but are far away from each other. So perhaps there is a similarity there between what we observe from the measurements and what we see here from the map as well. So if you want to take another example, for instance, here you have these 6 nodes. You want nodes 1, 2, and 3 to form a cluster, 4, 6, and 5 to form a cluster as well. And what you see here in the upper part, the network is what we call not balanced. And in fact, if you just let it evolve, the phases and in fact the frequencies do not synchronize. You can actually tweak the network into something that is balanced. And what you see here is basically only 2 curves. You see 2 curves because there are 2 clusters. So actually, all the oscillators evolve cohesively in the way that we actually want at this point. So okay, we have a characterization of how the structure affects pattern synchronization. Now the question is, how do we get from here to here? So I cheated a little bit. So I give you a network and say, okay, it works out, but how did I obtain it? And it turns out that this question is in fact fairly simple. So here's what we want to do. So we have an adjacency matrix, we have a network, and we want to modify some of the edges of this network such that there is a synchronization pattern that is beneficial, desired in some sense. So we want to go from our network A to a network that is A plus delta, where delta is my perturbation, and the new network, A plus delta, satisfies some pattern synchronization, so my partition P is synchronized. And I want to do something more though. It's not that I want to change any possible edge in the network. Maybe I want to constrain the action that I can I can take. Perhaps because I cannot do anything else, or perhaps just because I want to obtain something that is very sparse. So in that case, I want my perturbation delta to be structured, in the sense that maybe you want to, again, modify some of the edges, maybe you want to, you have some other constraints, so you have some constraint set over here. And on top of that, I mean, well, you don't want to rewrite the whole network from scratch. So you want to obtain modifications which are somehow small. Small quantified by a norm. In this case, we take the Frobenius norm. So you want to minimize the change such that your perturbed network exhibit a synchronization pattern that you like, and your perturbation must be of certain kind, structure kind. Okay, seems fairly innocuous, but there are ingredients here that typically make problems fairly difficult. For instance, this last one, obtaining a controller that is sparse. Is not as trivial. We all know how to assign the eigenvalue in a linear system, but if I want my controller to have a certain sparsity pattern, then the story is completely different. And in fact, there are many words there. So although it looks fairly simple, we have nonlinear dynamics that undergo behind it, and we also have structural constraints that make the problem intrinsically harder than what it looks. So to tackle this, let's have another intuition. So let's look again at our toy example. Here we have 3 clusters, again, the blue, orange, and green one. We can actually summarize this configuration into a simple matrix. So we can create what we call the characteristic matrix. It has as many columns as the number of clusters, and each vector in this matrix has a 0, 1, and it has a 1 when the node belongs to the cluster. So for instance, if you take the first column, you see a 1 in position 1, 2, 7, and 8, 1, 2, 7, and 8. So the first column corresponds to the first cluster. The second column has a 1 in position 3 and 5, 6, and therefore 3 and 6 are together. So there is a one-to-one correspondence between a graphical representation of the pattern that you want to enforce and a matrix representation. Not only that, if you assume that your network is synchronized, pattern synchronized, then the evolution, so the phases and frequencies of these nodes will actually have to belong to the image space of this matrix. Right? So for instance, you may have your phases which are pi over 3, and again pi over 3 over here, because those are cohesive. And you have pi over 2, pi, and pi. Well, this vector belongs to the image space of this matrix. And the same happens for the velocity, in fact, for the acceleration, for what matters, any derivative. So this matrix is in fact fairly important. It's in fact fairly important because it says, well, this network will be pattern synchronized if this matrix here defines an invariant subspace for the dynamics. So although the dynamics is nonlinear, we can still identify a subspace that describes the invariance properties of the synchronization property that we want to enforce. So we can actually show a little bit more map of where this comes from, but what is really important, I think, is that we can take our first theorem on how to modify and how to, the first theorem on characterizing pattern synchronization in networks, and translate it to a one that is actually useful for implementation of a controller. So instead of having this condition over here on the structure, I can actually enforce that the subspace defined by my characteristic matrix is invariant for some slightly modified network. So that's a static matrix. So you give me your network, you give me the desired pattern that you want to enforce, well, you can compute this matrix right away. And then what you want to do is to modify this matrix such that this subspace is invariant. So with this notion at hand, you can actually define a much simpler optimization problem. So you can take your structural constraints, bring it in your cost function, and substitute the fact that you want some pattern synchronization into an invariance property of a matrix. And again, this is, to me, quite surprising, because the underlying dynamics are nonlinear. But the only thing that I care about is basically a linear constraint here. So if I can satisfy this constraint, my network will be pattern synchronized for whatever pattern I want to enforce. Now, this problem may be infeasible for some patterns, but if your constraint set is large enough and you can modify sufficiently many of these edges, then you will have a solution. So we went from studying a problem of where we had a network with nonlinear dynamics, and we wanted to enforce pattern synchronization among these oscillators, to a problem which is purely structural and linear. Well, in fact, this is convex, and in fact, you can characterize in closed form what the solution is. Now, the solution looks a little bit ugly. You have to do a little bit of matrix manipulation. But all it does is to look at the orthogonal complement of that subspace and make the map on that subspace 0. So you just make a subspace invariant. That's all there is. And in fact, that's how you go from this network to this network over here. So if you see, for instance, from this manipulation over here, you modify some of the edges. For instance, this one went from 10 to 11, and then you added one that went from 6 to 3. So for instance, if you look at the incoming edges to 1 and the incoming edges to 3, you see that to 1 you have a total weight of 12 coming from 6, and from 3 over here you have a total weight of 11 plus 1, which is 12 again. So by using this approach, you actually made this network balanced. So again, I mean, the mathematical details may or may not be interesting at this point, but what is important is that you can actually do it. So you can choose in closed form the ways that you can actually do it. Well, if you remove the structural constraint, the final network will look very different, slightly different. But of course, it may be interesting in some cases. So let me pause here for a second. So that's what we have done. We have started from a network of oscillators with Kuramoto dynamics. We wanted to enforce pattern synchronization, that is the formation of some clusters, the dynamics of the network. What we determined is that the structure plays, in fact, a critical role, despite the dynamics being nonlinear. And what we have analyzed is that, well, you can actually derive a controller, which is sparse, so you modify only some edges, which brings a network that is not synchronized, pattern synchronized, to one that has the synchronization pattern that you desire. And by the way, this structural controller can, yes, be implemented by changing the edges, but can also be implemented with other methods, usual feedback methods. Those are sparse feedback methods. So the question now, I only have a few more minutes, so I'm not sure how in details I can go here, is that this is really nice, but is this sufficient? So is this helpful, first of all? And I will argue, yes, it is helpful because it gives us a little bit of insight. But if you actually look at the data that you gather from fMRI or EEG or other type of measurement, the situation is much more complicated. In fact, in this data, yes, if you start from a brain network, you see that there are areas that are more or less coherent. But this coherency is not 100%. So the definition of clusters is somehow more fuzzy than what I have defined. So there is actually a graded notion of clusters, and there is a measure of how much a node belongs to a cluster or not. And in fact, these clusters, they evolve over time as well. So you may have nodes that at one time belongs to a cluster, and then at a different time they belong to another one. So yes, while this analysis is insightful, I believe, there are still many other questions that needs to be answered in order for this to be applicable or useful in a more neuroscientific domain. So we have taken an extra step. And in fact, this extra step is how do we define notion of synchronization which are somehow more analog, more quantitative, rather than being binary, 0, 1. And this can be done. In the following sense. So suppose you have a cluster that is again made of 2 nodes only. You can write down the dynamics for these 2 oscillators. You can see again that there is, the natural frequency. There is a term that depends on the intra-cluster connections. And then there are terms that depend on connection with neighboring clusters. So if you want these 2 oscillators to evolve close to each other, well, what you want is definitely this term to be strong with respect to this other term. So you want the inter-cluster connection, within cluster connection, to be much stronger than the one outside. And in fact, by using standard theory, you can define an arc, an angle, that guarantees that the evolution of these 2 nodes will remain within that angle. And that angle depends on the difference of the natural frequencies and on the ratio between the inside and outside connections. Now this is nice, but this angle is very conservative. So if you plot it as a function, for instance, of the connections in the network, or as a function of the frequencies, you see some type of behavior which you don't really want to see. So for instance, as you increase this ratio, the gap between these two bounds is increasingly bad. And moreover, if you increase the frequencies outside of that cluster, well, the true behavior, the blue one, goes to 0, meaning that the nodes within the cluster are really cohesive with each other, but the bound really stays high. So this bound is really non-satisfactory. So what is going on here? And I think this phenomena is key. So when you increase the frequency outside of the cluster, the cohesiveness of the nodes within the cluster increases. Well, the first thing I thought is that, well, the cluster behaves as a low-pass filter. It's a low-pass filter because when the frequency of the outside nodes is very high, their effect becomes very small. And in fact, you can prove it. You can prove it because you can bound the nonlinearity of the Kuramoto model with a linear system. This linear system is stable, so you can plot its transfer function, and you can actually weight the effect of neighboring nodes, neighboring clusters, through the body plot of the transfer function associated with the cluster that you want to study. And even this, I think, is quite remarkable because the underlying dynamics are non-linear. So really what we're doing here is using an approximation, a linear approximation, that however captures the behavior that we observe really well. And in fact, if we incorporate this frequency-based analysis in our bound, here's what we get. It's exactly this yellow curve over here. So the bound that we obtain through this approximate linear frequency analysis technique is in fact coherent and converges very well together with actual behavior. So all right, I think I will stop here. Thank my students who actually did all of this work and the funding agencies to which this was possible, and take any questions. Thank you.
Any questions?
There's something especially at the end you almost said, but I didn't quite hear, so I wonder if you could clarify. As I understand your clustering and synchronization definitions, they're point-wise. Each point in time is that addition. When you're sort of in the space of maybe something more like an L2 norm over the period of oscillation or something is more in line with what you're looking for. Can you sort of clarify how your cluster definitions might actually extend in my direction?
Yes, so there are two parts. In the first part, the definition was point one in each line, and those are the structural consistency. In the second part is the difference that we're trying to find. So somehow it is the yellow thing, in that sense. So you want the two functions to be close to each other. So their difference will be close over time. Right? And the bound that I have with the transfer function, they don't give you an exact bound. So they give you an approximation of that bound. So we're still working on that to see if we can get sharper things. And honestly, this is very recent work that we've done. But from initial evidence, it seems that that's the actual effect that matters the most. So yes, the interconnection matters, having strong coupling and weak outside coupling, but also this third effect, how different the frequencies are between inside and outside nodes, matters a lot. And how much it matters? Well, it's given by this structure. Yes.
Okay, while Evan sets up again, one more question.
This is probably a very naive question. At the beginning, you showed this cluster of birds, and you talked about one cluster and then multiple clusters. I'm just curious your thoughts. I don't know whether that's due to something intrinsic within that network or whether it's due to some exogenous input that breaks apart the cluster into multiple clusters. So can you share some thoughts about the network is described and the intrinsic properties versus some unexpected transient inputs that can change the dynamics of the network you create?
That's a very good question. I think it could be both. So if you think of social networks, for instance, if you try to form opinions, everybody has its own preference. So that bias, the internal bias, will actually contribute to the formation of clusters. In the same way, you may have external agents that influence, or external factors that influence the network, and will lead to the formation of clusters. So it's all a matter of your internal measurements and your external measurements that will determine how these clusters shape. And and that may be the case for birds as well.
All right, well, thank you, Fabio, again.